In this short unit, we're going to look at the geostrophic balance, starting from flow scaling. It'll be similar to the previous units where we looked at continuity to get an estimate of the vertical velocity at basin scale, and we also looked at the W momentum equation at basin scale and time scales of roughly 2 weeks, and found that we can assume the pressure to be entirely hydrostatic. Starting again from our Navier-Stokes equations, we're focusing this time on the horizontal momentum equations, and we're going to rescale those again for basin scale, because we're going to use similar numbers to the previous unit. So starting from the U momentum equation, the V momentum is analogous to this, so there's no point in going through both of these. Plugging in for our velocity scale, again 10 centimeters per second, 1,000 kilometers, length scale, gravity is 10 meters per second squared. This assumption again for the horizontal eddy diffusivity at that basin scale, about 10 to the 5 meters squared per second. Time scale of a few weeks. Our density, we know density, around 1,000 kilogram per meter cubed. We're going to plug in for F, so this is a mid-latitude area, so you get about 10 to the minus 4 per second, and we have vertical velocities from the continuity equation about 0.1 millimeters per second, 10 to the minus 4 meters per second. We go back, we plug these in, and we can rescale the equations, and we find out that the order of magnitude of this term here, the acceleration, is 10 to the minus 7. The order of magnitude of all the advection terms is the same, the nonlinear terms, 10 to the minus 8. On the right-hand side, we have the pressure gradient, which we don't have a good way to evaluate the magnitude of, so we'll leave that for a second. You have your Coriolis scaling here, again at 10 to the minus 4 times 10 to the minus 1 meters per second gives you 10 to the minus 5, and all of the diffusion terms are the same order of magnitude, 10 to the minus 8. Now what we'll do is divide all these terms, because all we care about is the relative sizes, so we'll divide them all by the largest, which is 10 to the minus 5, the Coriolis term, and we get 10 to the minus 2 plus 10, that's acceleration, advections 10 to the minus 3, pressure gradient's unknown size, the Coriolis term is now 1 because we normalize it to 1, and 10 to the minus 3 is the order of magnitude of the diffusivity. So again, similar to the W momentum equation, we have a bunch of tiny terms, one large term, 1,000 times bigger, 100 times bigger than this one, and an unknown term. So for this to balance, that question mark term, the pressure gradient, has to balance the order of one term, which is the Coriolis. So that tells us that the pressure gradient is must be order 1 balanced quarter. So pressure gradient and Coriolis are the dominant terms, and I can come back to our equation here and basically scratch out everything except for those terms. So we're left with just these two terms right here from our U momentum. So we took U and V momentum, and we removed all the terms that were much smaller than these terms. But again, the important thing is that we're talking about a specific scale, right? We're talking about basin scale over a long time, okay? If we were to do the same analysis for a bathtub, or even for something like Buzzards Bay, you would find that that these other terms are much larger than they are here, and they're getting close to the order of magnitude of the pressure gradient and Coriolis, if not bigger, in which case we cannot ignore them. So this is a basin scale, large scale type endeavor. After crossing out the terms, we're left with these two equations. Our U momentum and V momentum become these very simplified equations right here, where you just have a balance of your pressure gradient, 1 over rho dpdx, and your Coriolis term, Fv. And in the V momentum, the Y momentum equation, the equation for V, we have the pressure gradient in the Y direction balances the Coriolis parameter here. Now note, in the X momentum equation, the top equation here, 1 over rho partial P partial X equals Fv, the velocity in there is the V velocity. And vice versa for the Y momentum equation, we have the pressure gradient in the Y balancing a term which includes the U velocity, the X direction velocity. And this sort of cross term balancing is going to lead to sort of this interesting phenomena in terms of geostrophic flow that we're going to get to in more detail in the next slide. Now, since we did this momentum, examine the terms of the momentum equation for base and scale, now do we have to repeat the same procedure for every different problem in order to determine if we can throw out all those terms and use these set of equations? And as I noted here, they're simplified to be accurate to about 1%. So you can capture all but about 1% of the flow dynamics at base and scale simply by solving these equations. If you're looking at across these time scales and these length scales at mid-latitudes. So rather than rescaling every time, we can just look at an important term, which is the relationship between the size of this term, u squared over L, which is your advection or your nonlinear term, and the size of this term, which is your Coriolis parameter here. Just look at the ratio of those two parameters, u squared over L and Fu. Just divide them. That's the order of magnitude of the nonlinear term. This is the order of magnitude of the Coriolis term. Cancel out the u's. And we get this parameter here, u over Fl. Again, F is the Coriolis parameter. You get this non-dimensional number here. So this number is dimensionless. It has no units. And this is known as the Rossby number. It's designated R naught. This number alone can tell you where your flow regime is. If the Rossby number is a lot smaller than 1, that means the denominator is much bigger than the numerator, which means the Coriolis term is much stronger than the advection term, and we can ignore the nonlinear terms. This is what will happen in our previous calculation where we had 3 orders of magnitude difference, so we had a Rossby number of 1 over 1,000, 0.001. But in general, for base and scale flows, and even some smaller scale flows, you're going to get a Rossby number much smaller than 1, meaning the flow is geostrophic, implying that the flow comes down largely to a balance between the pressure gradient and the Coriolis. That is a geostrophic flow. If we get closer to 1, meaning the nonlinear term and the Coriolis term are getting on the same order of magnitude, then we have a unity Rossby number, and now we're talking in the order of 10 kilometers or tens of kilometers, typically speaking, and that implies that we can't ignore the rotation and we can't ignore the nonlinear terms. We have to keep both of them in there. Now, if we get to bathtub scale, in this case, your velocities are still on the order of 10 meters per second, but your length scale is on the order of 10 centimeters per second, excuse me, but your length scale is now getting on the order of a meter, so that denominator is getting pretty small, and we're getting a ratio up there on the order of much larger than 1. In this case, Coriolis is small compared to the nonlinear term, and we can ignore the Coriolis. We can ignore rotation. So if we're studying flows in a bathtub, flows around a ship, I have some other examples here, you can ignore the effects of rotation. They don't matter at those scales, and length and velocity scales. So this is really where we are oceanography-wise, these two here, and it really depends what you're studying. If you're studying ocean basins, you can ignore advection for the most part. If you're studying Buzzards Bay or Clark's Cove, you cannot. You have to keep both terms in there.